Hello, everyone, and welcome to our 30-minute webinar called An Introduction to Solid Elastomers. Thank you for joining us. My name is Brian Graves, and I'm joined today with Matt Exline, who is our Engineering Design Manager. How you doing, Matt?
Hello, Brian.
Hello. And here's our agenda. We are going to talk about all things solid elastomers. We'll first talk about who we are, and then we'll dive right in the meat of it and talk about what exactly are solid elastomers. We'll describe to you the solid elastomer process. We'll talk to you about the advantages of using solid elastomers, and finally, we'll give you some examples of solid elastomers being used in the field. So, should be fun. But first, first thing I want to do is do a bit of housekeeping. So I'd like to mention that this webinar is going to be recorded, and a link will be emailed to you for future reference and for sharing. In fact, sharing is our favorite, so if you could share it, that'd be great. And secondly, we will be answering questions at the conclusion of this 30-minute webinar, and so feel free to submit any questions in the questions field of your dialog box there, and we'll be sure to follow up on any questions that aren't answered. So, and then finally, I would urge you to stay to the end of this webinar because we do have some bonus material I'd like to share with you that could be useful. So let's get started. Matt, can you talk to us a little bit about what Romeo RIM is all about?
Absolutely. Well, Romeo RIM is located in Romeo, Michigan, which we're about not quite an hour north of Detroit. We've got 2 plants here on this campus in housing 20 RIM clamps, with about half of them dedicated to our L5 process. These clamps range in sizes from anywhere from 4 by 8 feet up to 11 foot by 14 feet. We process polyurethane, DCPD, and LFI material substrates. And we just celebrated our 37th year anniversary.
That's awesome. So what can you tell us, what exactly is the solid elastomer? What is a solid elastomer?
Well, in its essential form, a solid elastomer is an elastic polymer, and you can go on Wikipedia and there's a much more in-depth definition of that. But essentially, it's a material or a polymer with the viscoelastic properties, which means when a load is applied, the material will deform, and when the load is removed, it will return back to its original shape once the load is removed from it. Is a general characterization for ease of understanding, kind of rubber-like characteristics in materials with relatively high elongations. This video is one of our solid elastomers in our bumper products, and it really demonstrates the viscoelastic properties or characteristics. So the impact load is applied, and once the event is over, the material returned back to its original shape.
That sounds like a pretty amazing material.
Yeah, our bumper stock is kind of special.
Very cool. Well, how would you describe how solid elastomers are processed? Let me get there. There you go.
Sure. Solid elastomers are processed in it's called the RIM process, reaction injection molding process, the way that we do them here. And the RIM process consists of 2 liquid chemicals coming together in a closed mold process at low temperatures. Our processing, our mold temperatures are right around 180 degrees Fahrenheit. Under a low viscosity, and that viscosity ranges somewhere around maybe the consistency of like maple syrup, all the way kind of down to water, more like like water. DCPD in particular tends to be a very low viscosity material. And under low pressures, our molding pressures are right, they vary depending on the specific materials, but around 70 psi or so. So it's pretty low pressure.
So assuming this animation shows us kind of the process.
Yeah, you can see the squiggly lines there coming together at the center mold. So it's showing the A and B components coming together and mixing at the mold, at the mix head, being injected into the tool. And when two chemicals chemically react, they form a solid elastomer, and the parts pulled out of the mold and trimmed up and ready to go.
Cool. All right.
Yeah, so, not all, there's no one material process that is a good fit for all applications, and our solid elastomers, are no different. But there is a sweet spot where solid elastomers in the RIM process kind of do make sense. And that is generally kind of medium to large size parts and kind of low to mid quantities. And what I mean by a medium to large size part, like 2 foot by 3 foot would be kind of on the smaller side for us. But then our parts go all the way up to, they could be 12 feet by 12 feet and 48-inch depths to them. The size can get pretty darn big. The volumes, our sweet spot for volume would be about 4,000 to 20,000 of any particular part. But we have plenty of application, plenty of projects where the volumes are 400, 500 a year. And we have several programs that are 40,000 a year and up. So there's a wide range, and a lot of it just depends on what does a part have to do. You can kind of see in this chart here, this graphics, where it fits really well. The larger the part is, and the more complicated it is, and by complicated, backside details, stiffening features, just unique odd geometry, that's where it starts to make sense. A simple flat sheet, it just wouldn't make sense. There's many other ways of making a simple flat sheet. The solid elastomers tend to kind of overlap in different processes and materials. SMC, kind of on the lower end of the volume or quantities per year. So if an SMC part for SMC had a low volume from their perspective, that would potentially be a good fit for us. And then RTM on the other end of small volume, if it's a higher volume RTM part, it starts to make sense in solid elastomers and the reaction injection molding process.
Okay, so I understand what a solid elastomer part is. It's got a lot of elasticity to it. I understand the process of two components mixing together in a closed mold, and now I know where the sweet spot is. So tell me what the advantages of using solid elastomer.
Sure. So some of the advantages would be B-side features and details, and those features being stiffening ribs, bosses, locating tabs, so you can locate adjacent panels or bracketry or something like that. So backside details, we're not limited to just a single nominal wall thickness part. The ability to vary wall thickness, so we can go from thick to thin, thin to thick throughout a part. I mean, there are some limits. We can't go too crazy there, but We absolutely can vary walls throughout a part. And you can do that to help hide, shrink, or rib read on a panel. If you kind of locally thicken or locally blend wall thickness up to a boss or something like that, you can help minimize the amount that you would be able to see it on the A side of the part. The ability to encapsulate. So we can encapsulate fasteners, brackets, stiffening features like bar stock, metal bar stock, or something like that. We can do in-mold paint with solid elastomers, and in-mold paint is a process where the cavity of the tool is painted the desired finish color. The mold's closed, the two chemicals are mixed and injected on top of this paint surface. And it's a chemical reaction. So it's a polyurethane paint with polyurethane behind it. So you get a chemical bond of the paint to the substrate. So it's virtually, adhesion is never a problem. You'll have to remove substrate before you would get paint to be removed. And what it does, obviously, is it saves that secondary step of getting something prepped, primed, painted, the cost of potentially shipping it to an outside paint source, things like that. And its durability is off the charts. Fastening or fasteners, we can do post-applied fasteners, in-mold encapsulated fasteners. We can bond stud plates, nut plates, other bracketry with fastening features onto it. Solid elastomers readily accept adhesives very, very well. And fillers, we can add mineral fillers, build glass fiber fillers, and adjust the percentage or type of filler to either modify the mechanical properties of the urethane to hit or satisfy the performance requirements of a part, and or to simply reduce costs, because the fillers are typically extremely inexpensive, and you're replacing polyurethane with this inexpensive filler.
Cool. Are there more advantages of solid elastomers?
Well, funny that you would ask, Brian. Yeah, solid elastomers, we can go really large parts. Our parts, I said, go anywhere from a couple of feet, 2 foot by 3 foot or so. We have solid elastomers that are pushing 10 feet with 1/4 inch nominal walls on them. Our tooling costs tend to be lower compared to SMC or injection molding, things like that. And that's mostly because of our low injection pressures and the relatively low temperatures that we run at. So since we don't have these high injection pressures, the tools can be thinner, they can be aluminum. The aluminum mold will be suitable for production for us. And it's just a less expensive, easier to produce, because you don't have to accommodate for all the heavy tonnage or high injection rates. I think our highest tonnage on our largest press, which is a 12 foot by 12 foot platen, I believe is a 200-ton press. And anyone who's familiar with injection molding would recognize that as a very low number for that size of a potential tool. And ultimately, what you get is the quality of an injection molded part. So crisp features, fine detail, nice finish to the part. But for more of a mid-range volume application, injection molding is great when there's a very large quantity of them being made. But typically when you get into these low to mid-range programs, it's difficult to justify the cost of injection molding when you're only making 500 pieces a year or 3,000 pieces a year or something.
Cool. So tell me about our tooling options. You mentioned they're low cost.
I did. There's basically 4 types of tooling that we'll recommend. P20 steel, that's pretty straightforward and obvious. It is produces a very high gloss, Class A finish. It does have the longest lead time for us. So, you know, it could be, well, I guess it's not, but nickel shell tends to be longer. But P20 steel is the most expensive route for us to go. You can do pretty much unlimited number of parts out of P20 steel in our process. Nickel shell, we'll use nickel shell when the part is really large, those 8-foot, 10-foot, 12-foot parts. If you were to produce a mold out of billet, aluminum or steel, just the weight of the block would be too heavy for our presses to pick up and our material handling equipment to move the mold around the plant. So nickel shell reduces the weight significantly of a mold. What you end up with is a shell of nickel forming the cavity and or core, and then it'll be either like an egg crate construction casting of aluminum, and it may even be an egg crate construction of plywood to make up the chase of the cavity and core. And aluminum, M1 aluminum tends to be that's kind of our go-to for almost every program that we work with. You can get very good polish to get the Class A finishes and glosses that we're looking for. And with any of these, but especially with aluminum, doing simulated textures, you know, leather grain, wood grain, basic bead blasting or steel shot, something like that, can readily be done in aluminum. It can be done in P20 steel as well, and you can do it in nickel shell, but changes to nickel shell tend to be much more difficult to accomplish. In prototyping, we use an epoxy mold, which, for lack of better terms, you're applying a fiberglass layer, typically maybe an inch thick or so, to form the cavity of the tool, and then the remainder of it, the block, is almost always plywood, egg crated up and bonded all in place. It works really, really well, as long as you only need probably less than a couple of hundred parts. What ends up happening is the epoxy cavity or epoxy core starts to delaminate the more heating and cooling cycles that the mold goes through. So when we do epoxy molds for prototypes, we generally would like to run them once. We'll run them one time, get as many parts as we can, and then move on. Making changes, so if we wanted to move a rib over, if we needed to add some features, changes in the epoxy tools are not real easy to do. The other prototyping method we've used is hand layup FRP or fiberglass, which you don't get any of the B-side details that we're capable of. It's more of a fit representation of the part, not so much a functioning part.
Okay, gotcha. Let's talk about a little bit of the characteristics of solid elastomers. I love these charts.
So this is a chart with some of the solid elastomers that we use, and you can see flex modulus or stiffness characteristics ranging anywhere from 25,000 psi up to over 200,000 psi. And actually, we have several others that we currently run that flex modulus is all the way down around 4,000 PSI. So fairly, very, very flexible to pretty rigid, all capable in a solid elastomer. Some of the other characteristics being good elongation. You know, our lower flex modulus materials tend to have higher elongation, which kind of makes sense. And then pretty good impact resistance at notched IZOD values of 11.57. That's pretty darn good.
Hey, Matt, do you want to see a video?
It depends on what it is.
I've got a great video for you. It talks all about impact resistance. You want to see it?
Sure.
All right, here we go. This is an 8-pound weight dropped from 40-inch height onto a solid elastomer part. Watch what happens. If I can get the mouse over there. Where is it? Okay, let's try that again.
Oh yeah, this was the Gardner impact testing James was doing.
Yeah.
So.
On the impactometer, right? Is that what they call it?
Yeah. Yeah, that would be that's Gardner impact. So that's just a different method of measuring impact.
I like impactometer better.
Sure.
Do you want to see another one?
Yes.
Do you want to see another video?
I do.
So now we're going to compare how RIM compares to this same test. Let's watch that. Let's kind of watch that. There we go. Same test. It blew right through it, huh?
Mm-hmm.
Yeah. So do you want to see another video?
Yeah. This is interesting stuff. I knew the results. I hadn't seen the video.
No, good. So this is going to, we tested also FRP material in the exact same test. So let's see what happens here. Well, yeah, blew right through it again.
Yeah, and that kind of goes with what we see out in industry as well. You know, FRP is a very inexpensive tooling method. Piece prices tend to be high, and it has its place in industry, but the properties of our solid elastomers really do a good job in environments where it's going to take an impact.
What about flexibility?
Flexibility is very important as well.
Did you want to see another video?
Yeah.
I've got another one for you. And just watch this flex. I'm wondering if that's a Fortnite dance.
Is that the Brian Graves elastomer? Is that
yes, that tests his flexness.
Brian elastomer? I don't know.
Yeah. So that's all the videos I've got. I hope they were helpful. Where are we at now? Okay, so now let's show them where solid elastomers show up in the field.
Applications, yes. This is a fender for a walk-in delivery van. It's roughly a 1/4 inch thick. It is about 2 foot by 3 foot, and this is a XGT 100 solid elastomer. It has really good impact protection or resistance. It's flexible, and as you can imagine, this is a commercial application with a lot of bumps and bruises, running in things, bouncing into stuff, road gravel, things like that. So the advantage for our customer was that we could in-mold prime this for them, so it reduced their total labor to get it color matched to the vehicle. Oops. Another application being in agriculture, we use a lot of solid elastomers in the ag industry, and mostly in fenders and other body panels for the exact same reasons that it made sense for the delivery truck industry. These types of vehicles tend to take bumps and bruises, run into things falling on them, backing into barns and stuff like that. With this particular one, we did in mold paint to color match to the customer's end needs. And another, you kind of start to see a recurring theme here of locations where you may run into stuff or things might bump into it. That's where a lot of the solid elastomers are used. This is a light pillar application for this customer. And we incorporated, this was actually a really good case study for us. This part was FRP fiberglass, and it had brackets and stiffeners and reinforcements all glassed in to get it to mount to this vehicle. Through our kind of collaboration with the customer's engineering group, we were able to commonize, consolidate, take parts out of the fiberglass part, turn it into molded features in the panel, and it ended up saving, I think it was over $120 in labor and time per bus. And this particular customer makes about 3,000 buses a year. So it was a huge savings for them. And the longest running solid elastomer here at Romeo RIM is our energy absorbing bumper systems. Our bumper systems are designed to take repeated 5-mile-an-hour impacts of vehicles up to 60,000 pounds and with no damage to the bumper or the vehicle.
Cool. Well, I think that covers the introduction to solid elastomers. If you are working on a project, I do have some bonus materials, so don't leave yet. If you do have a project, you can contact us by sending us an email simply to sales@romeorim.com or giving us a call at our local number 586-336-5800. You're welcome to send us your CAD model, either in SolidWorks, STEP, IGES, or Parasolid, and then provide as many specifications as you can in terms of your project, and any information as to the surrounding components would also be helpful. But we will do a really quick Q&A. I do have one question to ask, and that is there such thing as a thermoplastic elastomer? Elastomer.
Yeah, there is, absolutely. I think there's some nylons that would be considered an elastomer.
Okay.
It's not as, I guess, quite as common, but they exist for sure.
Okay. Well, in the interest of time here, I will just go ahead and move on to the bonus material that I mentioned earlier, which is we built a composite/material selection app. It takes you about 10 to 15 seconds to go through it, and it'll spit you out a short list of processes/materials that you can identify as perhaps possible solutions for your project. So that's available at romeorim.com/selection app. And we also have a infographic that kind of explains all the different processes/materials at a one quick glance. And that is actually available in your handouts. You can download that right from your GoToMeeting dialog box there. So go ahead and dial that. That is also available on our website as well. And finally,
Wait, I just want to make sure that they recognize that, yes, I've tested the application app, and no, every every question does not yield reaction, rejection, or never like a solid elastomer.
This is true. We have, obviously, this is not accurate. This is just meant to be a helpful tool. We do not push our product necessarily. If it's not needed, you don't need it. So no big deal. But please follow us on the socials, Instagram, LinkedIn is where we post a lot. We also have YouTube channels. Check us out there. We're posting content a lot. So give us a follow and share anything you like. It'd be fantastic. So thank you. It was a pleasure hosting this webinar for you. Hope you got a lot out of it. If you have any questions, contact us via email, sales@romeorim.com, or give us a call by phone, 586-336-5800. And that is all. Thank you so much.